Okay, so I'm trying to create this video lecture. I'm starting off here with the ending of lecture 6, which was what we were finishing up with the spin-spin perturbation Hamiltonian last time. So I just want to review where we were going. We started off trying to look at the magnetic perturbations to the standard Coulomb Hamiltonian to the hydrogen atom. And we found out that to leading order, there were two contributions. One was the relativistic correction to the kinetic energy, and the other one was a magnetic correction to the potential energy. And when those two came in, they came both in at the same order in alpha, which you can see in this expression here actually is alpha squared, because this leading order unperturbed energy E sub n with a superscript 0 contains an alpha squared inside it. So when we square it, then we add another 2 powers of alpha, and we say that's second order or subleading order, or alpha to the 4th contribution to the energy. And we went through this last time, how that we have highly degenerate states characterized in their energy only by a principal quantum number n when we were dealing with the simple Coulomb Hamiltonian. As soon as we turn on the fine structure Hamiltonian, then those n equals fixed levels split according to one new quantum number, the total spin j, which we describe as an angular momentum just as if it were L, except now it can have a 1/2 integer value, and in fact it will, because it's the sum of a half integer spin angular momentum and an integer orbital angular momentum. So it can be 1/2, 3/2, and so on. Of course, if L is 0, it has no choice but to be 1/2. As you see for the n equals 1 level, only j equals 1/2 appears. As soon as we go to n equals 2, we have L equals 0, giving again j equals 1/2. Different energy, of course. J is not the only quantum number. There's also this principal quantum number remaining, n. But also a new possibility at n equals 2 appears, the L equals 1, which splits into 2. You can have L equals 1 coupling to spin 1/2 and going down to 1/2. That's the second recurrence here of the j equals 1/2 possibility. Or you can go up to 3/2, and of course the multiplicity there, 2j plus 1, once again becomes 4. And so these 6 actually appear as these 4 plus these 2, and these 2, of course, appear here as these 2. Okay, and we see that in spite of the fact that they have different L, they end up in the fine structure Hamiltonian having degeneracy, because the degeneracy is only broken by j. That's review. Now let's continue on to where we left off last time. I spent quite a bit of time reviewing this spinning sphere model, and you can see in the lecture notes all the detailed algebra, physics and algebra that goes through extracting a Hamiltonian for that system, computing the magnetic field at any arbitrary distance away from this in the limit where the radius of the sphere goes to 0. And we found that there were two pieces. There was the standard long-distance dipole contribution that comes out, and then there was this compact delta function type term that appears only when the two objects, or when the sensor that senses the magnetic field is sitting exactly on top of the dipole that's generating that magnetic field. Okay, that's where we were at the end of last time, and we were now going to put the pieces together and assemble the Hamiltonian that describes the magnetic interaction between the nuclear magnetic moment, and in the case of hydrogen that's just a proton, and the magnetic moment associated with the coupled orbital and spin motions of the electron. So let's look at how that happened. Here's the B solution from classical physics. Now we're ready to substitute in. This is where we left off last time. The spin of the proton gives rise to a magnetic moment. Okay, the only thing that's new about this is that it has this G factor, G sub p, that's specific to the proton and tells you how to look up its magnetic moment if you know its spin. They're parallel, of course, but there's a scaling factor called G sub p that simply must be determined by experiment. Now, here's your B. We know our Hamiltonian has to be minus mu dot B, so I choose the B to be the B from the electron, and I choose the mu to be the mu from the proton. This is the proton interacting with coupled with the magnetic field from the spin of the electron. And now you can see all the factors that come together. Here's the coefficients that come from two things. There's a mu 0 over 4 pi, okay? There's the mu 0 for 4 pi that appears. You can see the standard factor that comes from the long distance dipole field from point dipole, in this case of the electron. But we see that it's the spin of the proton that gets dotted with the r hat, so that r hat now has become here. And you can see this nicely symmetric type picture emerging. Spin of the electron dotting with r hat right next to the spin of the proton dotting with r hat, as if the two were on a completely similar basis, even though here, of course, we considered them to be, one of them to be the source of the field, the other one to be the sensor. Once again, the second term, this is the not the contact term that a delta function, that's down here. This was just the z hat term from B that's now dotted with mu to produce a spin-spin interaction term. Now, let's not neglect the delta function term. Here it is. Again, it has the same spin inner product. And there's the delta function that selects the piece of the wave function where the electron sits exactly on top of the nucleus. Now, we know that if there's angular momentum, the probability that the electron will actually be located inside the nucleus is negligible, because there's a node in the wave function at r equals 0 if L is greater than 0. And so this term will go away. That's why I write down here for L greater than 0, only the first term survives. But now let's consider what happens if L is 0. Well, it turns out that for the L equals 0 term, the wave function is completely isotropic. Think of it as a YLM, as a spherical harmonic whose magnitude is simply 1 over square root of 4 pi and doesn't have any angular dependence on theta or phi. Now, in that case, you simply are going to do this integral. It turns out that you end up with, if you do this integral, the r hat dotted with SE becomes the cosine of theta to that, where theta is the angle between r hat and that vector. Here's the cosine theta prime, which goes to this one. Do the integral over all the directions r hat, and you get 1/3 times the inner product of SE dot SP. That cancels the 3. These two subtract to 0, and you end up with 0. So there's kind of a complementary behavior in this expression for this Hamiltonian. Either L is 0, in which case you only have the second piece, or L is non-zero, in which case you have only the first piece. And since we can get a perfectly sensible and good feeling for what this Hamiltonian does in any one example, let's just consider the n equals 1 case. There's the case where it's only the second term that survives. We end up with a 2/3 factor. Here are these coefficients that came along with it that express the scaling factors that go with the magnetic moments of the two particles. Here we see the inner product of the two spins. And here is the what the delta function does when you sandwich it in between two wave functions. You basically just select out the r equals 0 piece, and looking closely back, the Laguerre polynomial that goes with the ground state of hydrogen is just the polynomial 1, and it turns out that the radial piece looks like e to the minus something. It's an exponentially decaying radial wave function. Do that radial integral, and you end up with this total density at the origin of 1 over pi a cubed. Put that all together, and now we have to do this two spins. Now, remember before, whenever we have the dot product of two spins, we remember the little algebra that we went through when we did L dot S. We remembered that you could do L plus S and square it. Then you get two pieces that you know how to do very well, L squared and S squared. And then you get the inner product, L dot S, which is what you want to do. Okay, that's what you wanted. We're going to do that here. We're going to consider, instead of considering S dot S, let's consider instead a capital S, a big S, which is actually SE plus SP, the total spin of the electron-proton system. Square it. Capital S squared is equal to little se squared plus little sp squared plus 2 se dot sp. Well, I'm going to now isolate the se dot sp, move all the squares to the other side, and this is what we end up with. Big S squared. Well, what's an S squared operator? It is S times S plus 1, like any other angular momentum squared, with an h bar squared factor outside to get the units. So let's bring the h bar squared outside. Here's our S squared. Now we're going to subtract SE squared and subtract SP squared. Each one of those is SS plus 1, but they're 1/2. So 1/2 times that 1/2 plus 1 is 3/4. Subtract two of them, and you end up with S with minus 3/2. And here the algebra, I'm just canceling out some common terms, and it reduces down to this nice expression down here. This is an example of what you might be asked to do in homework or on a test. Apply the derived formula for the hyperfine structure and apply it in the n equals 1 state to get the shift of the ground state due to hyperfine interactions. And it depends only upon this the capital S quantum number, which we all know represents the total spin, can be either 0 or 1. Think about it. 0, because if the electron is spin up and the proton is spin down, and we couple those two to 0, then we're going to end up with 0. On the other hand, if we couple the two spins 1/2 plus 1/2 and we put them parallel, then we have a triplet state, which is the total S equals 1. Now, I don't mean to confuse that with L equals 1. It's just the way the two spin 1/2s couple together, they produce an integer. Okay, I think I'm going to pause now and break the lecture so that I don't run out of space on my video, and I'll take up with the second part having to do with interactions with external spins in just a moment.